Good morning, good afternoon, good evening, everyone, depending on where you are in the world. Welcome to Photonics for Quantum 2. And before I introduce today's speaker, I wanted to introduce you first to our sponsor, Rick Van Gorsel, ID Quantique, who's going to give a 5-minute or so talk. And following that, I'll introduce the speaker. Rick, go ahead and take it away.
I hope that you see me now.
We can see your screen now.
Okay, good. And now you should see my screen and the presentation mode. Thank you, Don, and thanks the organizers for this wonderful meeting. It was wonderful last year in January, and I'm glad that you having it again, even though it's virtual. I'll give you a very short introduction to ID Quantique. And I wanted to talk about our advances in single photon detectors and electronics. I'll try to keep it short, within 5 minutes. We are a spin-off from University of Geneva, the group of applied physics, already back in 2001. That time, the people from the GAP, they wanted to, they saw an advantage of using quantum technology, quantum physics in quantum communication. And that's what we set out to do. In order to do that, we had to develop a lot of our own instrumentation because there was nothing out there in 2000. Started in 2001 with our first near-SPAD single photon detector and our quantum random number generator ships. And since then, things have every year we have at least one product launch to keep ourselves going. And the last, like you see right now, is from 2015 and going to the future of 2025 for our quantum security business unit. And you can see that we wanted to launch a QRNG in a mobile in 2019. It has just been launched in May. And some other things have been actually advanced a little bit, like the quantum key distribution on the satellite is a little earlier. So this is the last slide is only for our quantum safe business unit. And what I want to talk about is our quantum sensing, which got a big boost, literally, by our collaboration with Arianespace, which is the contractor for the European Space Agency, which decided that rather than using electricity to ignite the rockets, they want to do optics, and in order to do that, they need something to look at the integrity of their optical fiber system. And they chose to work with us because of our long history in being able to having very low energy instrumentation, which is one of the criteria, and because our ability to bring things to the market. So for the space launcher, the rocket launcher, we're using our single photon detector as an SPD system, our electronics, the ID900 time controller and ID300 laser. Together that makes a system for the Ariane launcher. Okay, other examples of lab to marketplace, you're probably familiar, some of you are familiar with our SPAD detectors. You can see 4 on a rack in the laboratory, and it takes quite a while to get them into a rack-mounted, telecom-mounted rack. Same thing with the QRNG, which used to be a big box, and now it is just being launched in the Samsung Galaxy Quantum. Okay, few words about our single photon systems. Traditionally, we've been making SPAD, single photon avalanche for the diodes. More recently, the focus has been on superconducting nanowire detectors. We combine it with our timing electronics to provide quantum sensing solutions. And those solutions are both in material science, whether it's fluorescence lifetime, in material science, for example, quantum dots or nitrogen vacancy centers, quantum physics, and quantum communication, which is the core of our business. And of course, there are many other applications too, in automotive, in surveillance and defense, and oil and gas. So SPADs, SNSPDs, and electronics, those are the main areas of our technology. I will go over this, I will skip over the next slides very quickly because we don't have that much time. So the ID221 is a detector that many of you are familiar with. It's a SPAD detector at -50 Geiger mode. Very low dark count rate for it. Can go even lower with the same diode if you go use a Stirling engine cooling to -90, and that's what we did. We get down to less than 80 counts per second. The backdraw about SPAD is that they are slow and they have a lower quantum efficiency, single detecting efficiently than nanowires. So in the last few years, we have been focusing on the nanowire detectors, and you can see some of the characters here. We make detectors both optimized for communication wavelength and visible wavelength. We can make them broadband. We've been developing high-speed detectors. PNR, which is photon number resolving detectors, absolute for numbers, so you can, with 100% certainty, you can tell you whether you have 1, 2, or 3, or 4 photons. And polarization insensitive detectors. The timing device is our ID900. The very nice part about it is an active device, so you have 4 high-speed outputs. So, for example, for a presentation yesterday from Gregory, when he was talking about being able to control the spin, yes, we can do that because we can control with much faster than a microseconds, a few hundred nanoseconds. We can do conditional, based on your inputs, you can have conditional outputs. The next slides, I think I'll pace through it very quickly. It's just an overview of the SNSPD and what the characteristics are. You can check our webinar, in which it's extensively discussed. So it's all based on our ability to make our own wafers and detectors. And based on that, we have very high quality detectors and detection characteristics. So I'm skipping through it so that I won't take any time from Jacques. Just want to show you this graph. This is an absolute photon number resolving, which I know some of you are quite interested in doing. We're using it, of course, for our quantum communication system. We have Alice and Bob, and we want to avoid interception by Eve. So right now we can go up to 400 kilometers with the SNSPD system. The whole system is automated, so it's a turnkey. Time controller. 4 high-speed outputs for delay and pattern net generation. That's probably the most important thing for you. And that's the nice thing is you can use it at any level, whether you want to use the graphic user interface, whether you want to do programming in Python or MATLAB or LabVIEW, you can use it. If you want to use Skippy commands, you can use it. It has, on the left-hand side, it has interactive screens to set the parameters, whether it's for the TDC, time to digital converter, or your outputs, your digital to laser ratio, and you can have 4-fold coincidences as a 4-fold TDC. The 4th level of interaction is actually we have provided access to our FPGA through a graphic user interface for a PDF editor. So summary slides. So please go to idquantique.com to look at our webinars, which have a detail of each of the products and their applications, and you can always send an email to info@idquantique. Thank you.
Okay, Rick, thanks very much. If you could turn off sharing, please.
Yep, I'll try.
And Rick is a 2-time sponsor. He sponsored last year and also this year. I thank you very much for your continued sponsorship to be able to bring this kind of material to all our participants free of charge with no registration fee. So now I'll introduce today's speaker, who is Jacques Carolan, who was at MIT and I understand now is at the Niels Bohr Institute. So Jacques, you can take it away, and you have 35 minutes plus 5 minutes for questions. And we don't have an additional speaker after this one. On some days we'll have a poster speaker, but we don't. So if it goes a little bit long, that's okay too.
Okay, thanks so much for the introduction, Don. It's wonderful to be speaking to you folks all today. You know, it's a shame I can't be there in person. You know, I was there back in January for the first ever Photonics Quantum, where I tried my first ever garbage plate, the true Rochester dish. So I've had about a year to recover from that now, so I think I'm about ready for another one. So what I'm going to talk to you about today are quantum photonic processes to accelerate machine learning. And quantum photonic processes are systems which store information onto the quantum states of light and process that information using photonic integrated circuits. And what I hope to show you is by leveraging foundry processes, we have a really promising platform with which to realize a whole host of new quantum protocols, particularly at the intersection of quantum mechanics and machine learning. Okay, so I'm going to talk mostly about work I was doing in my previous group at MIT and also touch a bit upon what I'm working on now. Okay, so I think it's fair to say that quantum has kind of become mainstream over the past couple of years. A number of demonstrations which are now actually in newspapers. You need to read academic papers. The one that's, I guess, most notable in the past year is Google's demonstration of a quantum advantage. And what they purported to show is that a system of 53 quantum bits is capable of solving something that a classical computer cannot. So why is that interesting? Well, it's been conjectured for many years that if you can store information onto a quantum system and process that information, you can calculate certain things more quickly than you can using classical computers. But up until recently, that hasn't been able to be demonstrated, partly because isolating that information from its environment is a significant engineering challenge. So Google's demonstration of that is a breakthrough because of that. Now, of course, there are some open questions, notably, you know, how well can we push our best classical algorithms, and also, you know, how useful are these kind of near-term sampling algorithms? But from an engineering perspective, you know, it's really quite an impressive demonstration. And there are many different ways in which you can build a quantum computer, whether that's some atomic-like system that's trapped either optically, electrically, or in some kind of solid state environment, whether that's using some kind of superconducting circuitry, or as I'll talk about today, with photons. And I think the point here is that you know, and there are a number of companies that are putting serious amounts of investment, you know, at least over $500 million into building this in industry now, which is really exciting. So even with all this excitement, there are still a number of open questions. We still don't know how to build a universal quantum computer. And what I mean by that is we know how to scale up the number of qubits and reduce down the errors on those qubits such that we can correct for errors quicker than they can accumulate. So there's a number of interesting questions related to that. You know, questions around materials, architectures, types of devices we want to design. And that's really where I see academia sitting in this industry ecosphere at the moment, is solving these really fundamental questions which can then be scaled up. But even with all these open questions, I think it's fair to say that photons are a unique technology amongst all of these technologies for a few different reasons. The first is that photons can be used to transfer information between each of these technologies, okay? Whether that's the scale of meters, allowing you to build up something akin to a quantum cluster computer, or whether that's at the scale of the kilometers, allowing you to build up something like the quantum internet for networking. Second is that with photonics, driven in part by significant amounts of investment into classical optical comms, we now have access to highly complex integrated foundries where we can build highly complex photonic chips, which we can repurpose for quantum applications. And devices of this complexity and scale are really challenging to build in a university cleanroom environment. What's more, we can now access these using multi-project wafer runs, which are relatively cost efficient. And finally, another thing that I think is super interesting is that the same technologies we use for quantum applications can also be used for classical applications as well, whether that's low power optical computing, signals processing, or even imaging. I'll talk about some of these a bit later, but I think it's a really unique part of quantum photonics. So in this talk, what I'll do is I'll give an overview of some of the key building blocks we need towards realizing large-scale quantum photonic processes. And then I'll talk a bit about some of the systems engineering challenges we need to solve towards realizing these large-scale devices. And for the final part of the talk, I'll look a bit more deeply into the types of applications we want to look at as well, particularly focused around the intersection of quantum photonics and machine learning. Okay, so in its most general sense, a quantum photonic processor, in my eyes, brings together 4 key technologies into a single system. On the input, you need some kind of non-classical light generation, which is essentially going to encode the input to your computational problem. They can be the generation of single photon Fock states, they can be the generation of squeeze states, but some way of generating non-classical light. And then this non-classical light needs to propagate through some reconfigurable both linear optical circuitry and non-linear optical circuitry as well. That is essentially going to allow us to program different types of operations on this system. Okay. And at the output, we need to have some high fidelity single photon readout. And I think it's pretty exciting that we've heard some, we've heard some nice talks just previously about the state of the art in there. So let's just zoom in on the circuitry for a moment. To understand the photonic circuitry, all we need to know is that the building blocks for linear optics are things like beam splitters and phase shifters. And in the lossless case, each of these elements is described by a unitary matrix, where each element of the unitary matrix gives you some probability amplitude to transition from a given input mode to a given output mode. Okay, so here you can see the probability amplitude of 1 on square root 2, and here you have a phase from going to this mode to this mode. So simple matrix multiplication just tells you if you plug these guys together, large scale linear optical circuits in the lossless case are also described by unitary matrices. Okay, so we see that here. And we can go further than this. Another key element is the Mach-Zehnder interferometer, which is a phase shift sandwiched between 2 50-50 beam splitters. So if you put light into the top mode and vary this path length, this phase, and you measure the optical power in the top mode, you will see a sinusoidal variation in that optical power. So essentially, that allows you to build reconfigurable beam splitters if you can control this phase. And then we can go even further. In particular, a particular construction in this triangular construction of these Mach-Zehnder interferometers followed by a phase shifter allows you to implement any unitary operator on those optical modes, which means you can implement any linear optical circuit. And if you're interested in hearing a bit more about this, we recently put together a review article on this. And the reason this is interesting is because it means that if you can build this one device, you don't need to go and fabricate different devices for different linear optical experiments, which can take many months or years to design, fabricate and test, and that's if anything goes right. You can just build this one device and program many different experiments on this single chip. Okay, that's pretty good. And the key building block towards how we actually build these on chip is using integrated photonics. And with integrated photonics, What we use are things like waveguide devices, where we have a high refractive index material surrounded by a low refractive index cladding, which effectively confines the light on chip into a single mode. And there's a variety of different materials in which you can use, each depending on the application you're looking at, the particular wavelength range of your photons. And for here, for example, we have a silicon waveguide on a silica cladding. Passive control is enabled by things like directional couplers, where you bring the waveguides close to one another such that evanescent fields of the waveguides overlap. So by tuning this interaction region, you can tune the amount of light that couples across. It allows you to design a tunable reflectivity beam splitter. And we can also actually vary the geometry of the waveguide itself to build things like on-chip cavities. And that's going to be important for realizing things like filtering, but perhaps more interestingly, you can really start getting strong interaction of the light with the particular materials. You can see some funky nonlinear optical effects generating new states of light, for instance. And active control is enabled by actively reconfiguring the refractive index of the material. And there's many different ways in which you can do this, and each have a particular speed associated with them, and you can choose it based on your particular application. So here, for example, you can do some kind of thermal tuning, and you apply a current across the waveguide, and you tune the phase through the thermal optic effect. So what do the devices we build look like? This is the state of the art in this very large scale quantum photonic processor. We have our input waveguide modes and our output waveguide modes. So this comprises now almost 80 Mach-Zehnder interferometers. Each one is just a few hundred microns in length. You can see the path length there, the directional coupler, and then the phase shift on one of the arms. So this full device brings together over 500 optical components in just a few square millimeters of silicon photonic chip. And we can also start including things like micro ring resonators, which are going to allow us to do wavelength dependent routing. As you operate devices at this scale, this then becomes a serious systems engineering challenge, right? How do we control both electrically, optically, and thermally this kind of device? So when we have many optical modes, we need to get light in there. We've had to design new kinds of fiber arrays to couple the light in and out of the chip. Electrical control is always a significant challenge, both the electrical routing on the actual silicon photonic device itself, routing out to a carrier PCB, and then out to your control electronics, and doing that with very low electrical crosstalk, and also the thermal management as well. How do you control the temperature on this chip? What we actually do is we glue this chip to a Peltier cooling device, which is actively monitored to monitor that, controlled to monitor that temperature. And we've been working with many of the folks actually at RIT and with Stefan Prebel to do part of this packaging, which is an amazing collaboration. So that's just an overview of some of the circuitry, but let's talk a little bit about how we want to do both non-classical generation of light and also this nonlinear light-matter interaction. And the reason we care about nonlinear light-matter interaction is because we need to get strong photon-photon interaction to realize things like controlled quantum gates. So what I'm pursuing at the moment in the Niels Bohr Institute is actually realizing these strong optical light-matter interactions through 3-5 semiconductor quantum dots. And the way it works is that you have a low bandgap material, such as indium arsenide, embedded in a higher bandgap material, such as gallium arsenide. What that effectively leads to is a strong quantum confinement and a discretization of the energy levels for electrons and holes. So you effectively have an on-chip artificial atom. Okay? And when you combine this system with nanophotonic structures, such as photonic crystal waveguides or photonic crystal cavities, you can really engineer this spontaneous emission into a particular mode of interest. So now, using these types of devices, you can really have some of the most highest performing single photon sources. Recent demonstration by some of my colleagues where they show they can get visibilities of over 96%, extending out to hundreds of photons. And from the given that you've excited your two-level emitter, the probability that it ends up at your detector is now about 14%. And there's a clear path towards pushing that efficiency up towards about 50%. So as well as having highly efficient single photon sources, we can get incredibly strong light matter interaction at the single photon level, which means we can do single photon switching through a saturation effect of this two-level emitter, enabling switching just at a few photons per lifetime regime, which is really exciting. Now, in this two-level emitter picture, it turns out two-level emitters actually aren't sufficient to do high fidelity photon-photon gates. You need another level. Okay. However, quantum dots can actually do this as well. What you can do is load a charge onto the quantum dot, so you get a charged exciton, and then you essentially have access to spin states. So then potentially you have a path towards doing high fidelity photon-photon gates through this spin-mediated state. Or you can do things like generating cluster states of entangled photons. Now, this is all well and good, but there are a few challenges with quantum dots. So the first is that there's large amounts of spatial variations, say on your gallium arsenide wafer, of where the quantum dots will be. And if you want to think about integrating that within some large-scale system, that's going to be a significant challenge. Another challenge is that there is variations in the central spectrum, the emission wavelength of these quantum dots. So if you want to do high fidelity quantum interference between dots in parallel, that's going to be a challenge. You need some way to select for particular emission wavelengths. And finally, is how do we integrate these devices within foundry scale photonic integrated circuits? I think one really promising approach towards looking at this is through hybrid integration techniques. And the way it works is that you get, say, your 3-5 wafer and your foundry photonic circuit, and you transfer from the 3-5 wafer onto the photonic integrated circuit using some kind of, as shown here from the wax group, some pick and place type transfer process. So here you have your tungsten probe, pick this guy up through van der Waals force, and then you place it on top of your waveguide. And if you can engineer the dimensions of both your, say, silicon waveguide and your 3-5 waveguide, you can get highly efficient transfer of light between the quantum dot and your photonic integrated circuit. And what that essentially allows you to do is means you can pre-select quantum dots that have a very specific requirements on both the frequency and bandwidth, and only transfer the ones over which meet these particular requirements. Secondly, you can think about then using your photonic integrated circuit to actually control these quantum dots. You can think about applying strain fields through, say, for example, electric fields on your photonic integrated circuit. Or you can look at applying Stark tuning to this as well and actually move the emission wavelengths. They can really be aligned for high fidelity quantum interference. And what I've shown here, to be totally frank, is a fairly arduous process. And if you want to think about scaling this up to hundreds or thousands of emitters, you really need to look at another approach towards doing that. But that's not crazy to think about. And we can consider doing some kind of wafer-wafer bonding approach, which is really the same type of methods that people are using to bring lasers onto things like silicon photonics. And also note there that it's the same types of material, 3-5 materials, that you want to bring onto your photonic integrated circuits. So there's a really exciting opportunity towards doing that. And if you're interested in hearing a bit more about this, we've recently put together a review article on hybrid integration methods in Optica just a few months ago. Okay, so I've just given a bit of an overview of some of the particular hardware towards building these large-scale quantum photonic processors. But I think it's critical that as you scale these systems up, you really think about the types of applications you want to run on these processors, right? Because, you know, these applications are going to be essentially inspired by your particular hardware, and that in turn will feed back and guide your hardware development, okay? And the idea is that you want to scale up your hardware and essentially scale down your protocols, you know, so you can effectively do more with less, and you can meet somewhere in the middle. And that's how you're really going to demonstrate practical quantum technology. And I think this is particularly important because many physical hardware have very unique features, and you want to take that into account when designing protocols and algorithms. I'll give you an example. Because in photonics, one of the key error mechanisms is loss. You know, we don't see the types of Pauli errors, bit flips, that we see with other types of, say, solid state quantum information systems, but we can lose our photons. So we need some way to correct for this photon loss. So one really promising approach is to encode a single qubit of information across multiple photons, such that if the error occurs, the information can still be recovered, okay? So I'll give you an example. What you can do is store your logical 0 in the state 40 plus 04, okay? Where 40 means 4 photons in your first optical mode and none in your second optical mode. And I should note at this point that I haven't specified the particular optical mode. You know, this could be frequency modes, this could be spatial mode, this could be polarization mode. This protocol is agnostic to the particular mode we want to use. And then you can encode your logical 1 in the state 2-2. And what you can show is that if you can realize this particular operation, you can correct for single photon loss without measurement and without a quantum memory. It's what we call a one-way quantum repeater, okay? So that's all well and good, and I can write down, you know, this operation, what it should look like, but I think it was really captured nicely in a beautiful paper from Miyato and his colleagues in the Lutkenhaus group. And what they said is, we do not yet understand how to determine if a given Hamiltonian can be implemented by arranging a reasonable number of optical components, right? I can write this guy down, but we don't know how to actually build it. It's a really interesting question. What we want is some way in which we can, say, train our quantum system to realize this particular operation. And when you couch it in terms like that, it began to sound a little bit familiar with a particular computational model that some of you folks might be familiar with, and that's neural networks. And the idea of neural networks is actually pretty simple. You know, it's a computational paradigm that has really seen a state-of-the-art performance in speech and language recognition, image recognition, many things like that. And it's inspired by signaling within the brain. And the idea is that you want to realize a particular input-output configuration over some large vector sets. You essentially train your system to implement the operation that takes, say, grayscale pixel values of a cat and outputs to the vector of a cat, say 1, 0, 0, 0. And what's going on inside is that you have some input vector, which encodes your input information, and then you perform a linear matrix multiplication, okay, which is parameterized by some weights, and then you perform a single nonlinear operation on each of those modes. And you repeat that many times. One of this is 1 layers. And you want to jiggle about these parameters such that you can realize this particular input-output configuration. So the idea is, can we do something analogous to this, but instead of discovering the operation that takes cat images to the categorization of a cat, pun intended, can we do it with, say, quantum state? Find out how to take this quantum state to this quantum state. Now, there's reason to believe you might be able to do this with optical systems, just purely in the classical regime, because the systems that I've been talking about, these optical photonic circuits, they do matrix multiplication on those optical modes. So if you can use that in the core of a neural network, you can potentially have a very high speed, where you have hundreds of gigahertz of photodiodes, and low power, if you can have quasi-static phase tuning, categorization neural network machine. And some of my colleagues recently proposed this architecture and did a proof of concept demonstration to show that these photonic systems perhaps are well suited to doing this. And there are a number of companies that have been set up to really explore this. Now, going back to our quantum application, I'm a quantum guy. And if I see something cool that's classical, my immediate reaction is, how can I make it quantum? So then we started thinking about, what is this quantum analogy of this optical neural network? And this was the architecture we came up with, a quantum optical neural network, okay? And so this is just in simulation, it's just a computational exploration to see what types of operations these systems can do. And the architecture looks like this. You have some single photon Fox state input, which goes into your circuit. Then you have some kind of linear transformation that's going to be described by your unitary matrix. And then you have some kind of nonlinear operation. In this initial exploration, we looked at just a monochromatic, very strong Kerr interaction, where the phase on each photon grows quadratically with the photon number. I'll talk a bit about how realistic this actual nonlinearity is. And then we repeat this for many different layers. And at the output, we read out the photon number. So we want to understand the types of operations this thing is capable of doing. So how do we go about training this type of system? Well, this whole system is just described by some large matrix in the multi-photon basis. And what you want to do is take some set of input states to some set of output states. So you can just define a cost function which quantifies that distance, summing up over all of those states. And if you minimize this cost function, then you know you've implemented the operation over the set of input states. So as a test, we can look at a variety of different things. The first thing we looked at was, can we do some kind of black box quantum simulation? So you give me your favorite Hamiltonian, let's say the Ising Hamiltonian, and you can exponentiate that to some time t, and that gives you a unitary. And we want to train our system to implement that particular Hamiltonian. And what we see is something interesting. As we increase the number of layers, we actually decrease the error in implementing that particular Hamiltonian. Now, in neural networks, that's actually a concept we're pretty familiar with. It's a notion known as expressivity. Deeper neural networks are capable of expressing a richer class of functions. And what we see now in the quantum setting is that deeper quantum optical neural networks are also capable of expressing a richer class of Hamiltonians. We also looked at the system for a reinforcement learning problem, where we actually learn to balance a pole on top of a cart. What we're doing is learning on classical data. So it's, I think, at least interesting we can learn on classical data. I'm not saying we get some kind of quantum speed up for this example, but it's these types of experiments we want to do to really understand where a quantum speed up might in fact take place. then, in fact, we can realize this one-way quantum repeater. So here, plot the output state cost to realize this particular operation to correct for the single photon loss as a function of the number of layers. So what you can imagine having is one of these mini little quantum optical neural networks sitting at different nodes in some kind of quantum networking system. So the nonlinearities we looked at are still highly unrealistic. This monochromatic kernel linearity that's ultra strong, doesn't really exist in nature. Okay, you're going to get some kind of losses. You're going to get some distortion of your pole shapes. So I think a really interesting research direction is understanding what we can do with realistic nonlinearities. And actually, this quantum optical neural network might be a really interesting architecture and framework with which to understand the types of operations we can do with these kind of noisy nonlinearities and noisy quantum photonic systems. And this idea of looking at noisy quantum systems has been looked at a lot in the past few years, and it falls under this guise of noisy intermediate scale quantum processors. And after understanding that building a universal quantum computer is a really significant challenge, people have been exploring what we can do with, say, a handful of qubits, say 100 qubits, that have a relatively few quantum gates, say of the order of the number of qubits, where the error on those quantum gates are above threshold. And just to give you a sense of how in vogue this kind of noisy intermediate scale quantum processors are, I think it was at APS March meeting, not the most recent one, but the year before, considering this phrase was technically invented in 2018, the preceding March meeting, there were 5 sessions devoted to NISQ algorithms. Okay? And they kind of fall in a few categories. One is just showing some kind of quantum advantage, showing you can do something that a classical computer cannot. And that's really what Google have been looking at through this random circuit sampling, and many optical teams are looking at through boson sampling. And then there's actually trying to do something useful. And these really come into these variational type algorithms. And there are many companies that are really pursuing these quite aggressively to show some kind of near-term quantum advantage. But there's something interesting. If you look at many of these algorithms and protocols and kind of squint, they all kind of look the same. And what it looks like is that you have some kind of input state which passes through a quantum circuit, and then you have an output state. And what you want to show is that sampling from some output distribution defined by this input state is classically hard while quantumly efficient. So for example, here, X might be the set of bit strings in the computational basis. So recently with some of my collaborators, we became super interested in the question, which is kind of the reverse of this, okay? Which is, given access to psi out, this output state, what can we learn about the system that generated this? Okay, well, why are we interested in that? Well, there's a few reasons. The first is just a pretty fundamental reason, right? Now, what are we able to learn from quantum systems? In particular, for many classes of these quantum protocols, it's not clear what information you'll get from these quantum states. Okay? Part of their complexity proof is that these quantum states essentially look like white noise. So what can we learn about the system? The other one is more of a practical application, which is essentially, this might allow us to be able to verify a quantum processor is actually doing something, right? If you're going to spend tens or hundreds of millions of dollars building a large-scale quantum system, it sure as hell better be doing something classically hard. And this can be a way to actually verify that. So just to formalize this notion, the question we ask says, given knowledge of the input state, psi in, and access to the output state, psi out, learn an operation which efficiently returns psi in. In other words, can we unravel the action of an unknown unitary on a known input state and learn the inverse of these black box dynamics? Just to give you an analogy that hopefully some of you folks will be familiar with, it's really like trying to take a garbage plate and figure out what the constituents are of the garbage plate. Okay, and of course, where this analogy breaks down is that we know that all of the components are actually in this garbage plate. So naively, one thing you might want to do is take a quantum circuit where you can well control the parameters, feed this output state into that quantum circuit, and maximize the overlap between the total output state and the total input state. Or in the language of machine learning, we can define a loss function, 1 minus that overlap. And if you minimize that loss function, I maximize this overlap, you've essentially done the inverse over this single input state. You know, you found U dagger, we implement U dagger. And there's an immediate reason why this won't work, which is that on average, this cost function scales as 1 on the dimensionality of the system. Why? Because you're trying to find the overlap between two quantum states in Hilbert space, and Hilbert space is exponentially big. So on average, that value will be exponentially small. So that's a bad thing to do. So the real challenge is essentially to select efficiently accessible subsets of Hilbert space with which to do this optimization. So the approach we came up with, we call variational quantum unsampling, okay? And it's essentially inspired by neural networks. It's a layer-wise approach of tackling this problem. So let's imagine our input state was the input state of all zeros, and it passes through some complicated quantum circuit, and that gives us our output state. In variational quantum unsampling, what we do is we pass that n-qubit output state into an n-qubit quantum circuit and vary the parameters to find the first qubit in the state 0. And once we've done that, once we found that deterministically found the first qubit in the state 0, we've essentially unentangled that qubit from the remainder of the state. And then we can go into the next stage. Okay, now we get the remaining n-1 qubits, we pass that into an n-1 qubit circuit, and we vary the parameters to find that second qubit in the state 0. And we repeat this for a total of n times. So what can we say about this? Well, now this loss function scales as a constant in the number of qubits. On average, it's going to be 1/2. Why that's the case? Well, you're looking for the first qubit to be in the state 0, and half of all, just from a counting argument, half of all the qubits in Hilbert space have 0 as their first element. So verification looks twofold. First, you can just go and inspect these V's and see if it's the related to the U that you thought you were dialing. And if it's not, you can perform some kind of reduced tomography on a subset of these qubits. So, you know, I haven't said anything about how you actually implement and realize these particular V's. And in general, doing an arbitrary n-qubit operation scales exponentially bad. Okay, you need an exponentially deep quantum circuit. So what you're going to have to do for your each unsampling protocol is to leverage unique structure in that protocol, in a particular sampling algorithm you're looking at. And for ones with very little structure, such as random circuit sampling, it's unlikely you'll be able to do this efficiently. But we believe for a large class of interesting algorithms, there are efficient unsampling protocols. And we give at least one in the appendix of our paper. So we then implemented this on a photonic quantum circuit, where we take photons generated by spontaneous parametric down conversion, we feed that into one of our reconfigurable silicon photonic chips. You can see here, we outcouple those photons into a superconducting detection system, and we feed back onto the chip. And the chip has so much kind of versatility and such a large number of tunable phase shifters that we can use one part of the chip to do the sampling operation and the other sections of the chip to do the layer-wise unsampling operation. And what we see in the first stage, we want to find the first photon in the first optical mode. We jiggle about our parameters for our first layer, and we reach the noise floor of our experimental system. And then we move on to the second layer. We don't even touch that first photon anymore. We vary our parameters and we find the second photon in that, which is back to our input state. And what this can potentially be is, a way to do verification on verification and characterization on large scale quantum systems in a variety of different platforms. And we expect to see other variational quantum unsampling protocols in different platforms other than photonics. So in the last just 2 minutes, I just want to give a bit of a perspective on where I think some really interesting research directions to go moving forward. What I'm hoping that we'll see is that we'll scale these optical matrix processes up to the regime of hundreds of optical modes, in part accelerated by significant amounts of investment into these optical neural network companies. That's going to enable new paradigms for optical machine learning and things like optical FPGAs for signal processing. They're really interesting classical technologies that are going to be developed here. As we start pushing these quantum photonic processes in the next few years, I think it's very feasible to imagine tens of photons with some kind of nonlinearity. And that might enable new kinds of molecular quantum simulations to simulate vibrational modes of different molecules and enable us to develop new quantum machine learning architectures as well. Hybrid integration is a really exciting opportunity to start bringing in not only things like quantum emitters, but new kinds of material. Can we think about integrating phase change materials for quasi-static phase tuning, or interesting electro-optic materials to do electro-optic modulation for fast, low-loss modulation in these types of systems? And finally, as we bring all of these together, we really start to bring the losses down in our, say, quantum dot emitter systems. We can start pushing these systems into the ultra-high cooperativity regime, which is going to start enabling quantum repeaters. And ultimately, if we can do this, we can think about realizing loss correction on these systems as well, which might be a path towards universal quantum computation. So there's a number of folks which I want to thank who are involved in this work, both at MIT and the University of Copenhagen, and also in industry as well. Collaborators at Google and Zapata, and also photonics companies who work closely with Elenion and Light Matter. And want to thank all of the funders, and I will thank you for your time. Be delighted to take some questions.
Okay, Jacques, thank you very much. I'll clap for everyone. And let's see, I don't see any questions in there yet, but I actually have one, and I'll go ahead and paste it in there. And so hopefully you can see that.
Yes, let me look at the chat. Oh, I see, great. Okay, so, oh God, they're all coming in now. Okay, what would be the value of having on-chip room temperature single photon resolving detectors? What operating frequency would be required? I mean, that would be absolutely great to have on, room temperature single photon detectors, particularly if they can be integrated within our photonic system. The operating frequency, if you mean the kind of wavelength that we care about, that's a really interesting question. And it also comes down to the types of photons we want to generate as well. if we're using quantum emitters, the best quantum emitters are really around the 900 nanometer regime. So you're going to want to be detecting around there. Now, of course, that's not compatible with silicon photonics. You're going to start absorbing them into the band gap. So what we want to do is start pushing our emitters down, up towards telecom wavelengths, and that actually is possible. There are, telecom quantum dots are really coming on pretty significantly now. So I think there's a huge amount of value towards having room temperature detectors, in particular photon number resolution. Is going to make all of these quantum machine learning protocols just all that much easier. So I think that's a great thing. If someone can start doing that, that would be awesome.
Okay, actually, thanks for talking about wavelength, but because I should have asked that also, but I was actually thinking about the repetition rate, like how quickly does the bandwidth, how quickly does it need to process photons?
Great, yeah. The quicker is always better, but we don't need to go so fast. I mean, the lifetime of these quantum dots is about 1 nanosecond. So you really can't think about going faster than a gigahertz.
Okay, that's fantastic. Yeah, I just wanted a ballpark. It looks like there's another question from Shuo Sun, which is a couple comments down. If you could take that one on.
Okay, so I'm just going to go in order. What are some of the limitations of quantum photonic processors from Arslan compared to other solid state alternatives? So, the limitation of this system is always loss. We have flying qubits, okay, and that's very different from thinking about, say, some atom-like systems such as NV center, which is going to be static and you're going to perform operations and build up entanglement across there. So it brings some really interesting and actually very unique hardware requirements. Okay, the way we're going to build up, say, a large-scale quantum photonic processor, is on the fly, is building up entanglement and entangling these different photons together. So you need to. So the challenge there is you need to be able to process your electronics, detect a photon, then perform some operation, while your other photon is still alive. Okay, so you need to do very quick, on-the-fly classical logic. Okay, which probably for all quantum computing architectures you're going to want to be doing this, but for optics, it's even more necessary. However, one of the really exciting things is that there are now some really good loss correction codes that work for photons. So I can point you towards some of the work from Terry Rudolph and Mercedes Gemea Silva, where they show how you can do loss correction on photonic qubits. If you can build a 3-photon GHZ state, that's essentially your result. So if you can press a button and get a 3-photon GHZ state, then you're good. So there are challenges, but there are also unique opportunities as well. Okay. Yeah, okay, great. So I'm just gonna go ahead and ask the next question from Shuo Sun. Can you elaborate on the potential physical mechanisms to implement the nonlinear phase shift you described in the quantum neural network? I'm very glad you asked that question because I actually do have a slide for that. It's the elephant in the room. Okay? How do we get strong photon-photon interactions? It's always the challenge. And there are a number of different ways in which you can do this. So optically, you can think about doing some kind of measurement-induced nonlinearity, where you measure the photon and you feed back to an operation in the chip itself. The challenge there is that this is probabilistic. And to turn it into something near deterministic is really, really hard. So maybe that's good for near term, where you don't care about like super strong rep rates just for proof of concept, but it's going to be a challenge. It's not the way to go. There's some really interesting approaches towards looking at doing this all optically, where you have some kind of Chi2 or Chi3 nonlinear material, and you build an ultra high quality factor on ultra high quality factor and very small mode volume cavity around this. And these two papers and many others have actually shown that if you can do this, you can really think about potentially having strong photon-photon interactions. The Q on V values are pretty aggressive, and we're not there yet, but it's really interesting approach. The other way is to do some kind of superconducting cavities. These superconducting resonators, these actually realize a Kerr nonlinearity. So then your photon is going to be a microwave photon. That's also fine. We don't mind. Or you can think about having some kind of atom mediated. And I think that's what I'm super interested in the moment is, can we use these quantum dots to realize these photon-photon interactions? Okay. Just scrolling down. Okay, from SHC. If we want to do practical processing, in your opinion, at least how many MZIs should be on one photonic chip? Wow, great question. So I would say, the more MZIs you have, the more loss you have. So while you might be able to get significant, significant numbers of MZIs, ultimately, if you make it really, really deep, your photon's not going to come out. But just to give a ballpark figure, we think at the regime of kind of non-classicality, you're going to want about, I don't know, say 20 photons in, say, 100 optical modes. That's what people think about. Doing 100 optical modes, 100 by 100 matrix operation is probably pretty challenging, I would say, from the electrical control there. But I think there's actually interesting applications if we can get to, say, 10 mode interferometers with multiple layers. So if we can have 10 by 10 and maybe have 5 layers, so we have 100 in each layer, and then that's about 500. That's gonna, I think, do something interesting. Now, ultimately, we're gonna be limited by the non-linearity. We're always going to be limited by the non-linearity here. But if we can get to a few hundred controllable MZIs, that's going to be awesome. And we're not even that far away at the moment, which I think is really exciting. Okay, from Zhudong. In simulating evolutions, how would a photonic processor do with regard to a more classical Hamiltonian versus a quantum Hamiltonian? Think of a longitude field Ising versus a transverse field Ising Hamiltonian. Okay, so I'm not super sure I understand this, but I'll think about the best. It really, we're really ambiguous to, to the type of Hamiltonian we implement in some sense. All we're doing is that if you can describe this guy in a Hamiltonian, then we can write down a unitary. All we're doing is implementing that unitary on our photonic chip. In principle, it absolutely should be able to do a classical Hamiltonian as well. Now, do I expect to see any speed up over simulating this classical Hamiltonian, on a classical computer? I have absolutely no idea. That's a really interesting question. In terms of this notion of speed up, if this is where this question is pointing towards, in some sense, we're getting a kind of speed up for free by cheating, because what we're doing is we're, operating on quantum states. So there's no real efficient analogy for operating on quantum states. Now, of course, the question is, how do you generate those quantum states? And that's a big open question in quantum machine learning. How do we get our encoding into our quantum states? And we don't purport to solve that here. So I think that's all the questions that I can see.
Okay. I think that's it also. Thanks very much, Jacques. And tune in tomorrow. We have a talk by Andy Weiner. And preceding that talk, we have another sponsor talk. And tomorrow, for the first time, we'll have a short presentation after the science talk, it'll be a poster presentation. So look for this recording on the PFQ2 website. It should be up later today. And otherwise, again, good morning, good afternoon, and good evening, wherever it is for you. And so long. Thank you.
Thanks so much, folks. Bye-bye.